All right, welcome back to class, everybody. Today is the beginning of the second week, and we're going to start with Chapter 2 in Bioenergetics. Before we begin, I just want to go to our Brightspace website and just show you some of the additions. So if I go to the home page for Exercise Phys and I go to Content, I just added one of these little tabs here, Spring 2021 Lectures. And these are the two lectures that we've done already. So they're on YouTube and you can watch them as many times as you need, and I'll get today's lecture up as soon as we're done. Before we begin, does anybody have any questions or anything that I can address? Anything like that? If you have any questions as the lecture for today is going, just feel free to come on mic and ask about it. So today what I'd like to do is go over Chapter 2, but before I begin Chapter 2, I want to give you some information that might be helpful. So if you can, I want you to go to this website here, health-calc.com. So everybody just type that into your browser. So when we're talking about bioenergetics, what we're talking about is the energy for a human body to function. So let me just open up our PowerPoint. All right, so this week what we're going to be talking about is fuel. And like in a car, the fuel for a car, to get a car to go, is gasoline. And your body is somewhat similar. I mean, it's a moving, I guess, biochemical system. And that biochemical system is going to need some type of gasoline, something. So we refer to the fuel that the body uses as bioenergetics. And muscle metabolism, meta. Meta is like a sum of, and bolism is like creation or breaking down. Like there's catabolism and anabolism. Anabolism is the building up of stuff. That's where you get the word anabolic steroids, because anabolic steroids build up protein. But then there's also catabolic processes that break things down, like the breaking apart of adenosine triphosphate into ADP and to phosphorus, and the release of energy is a catabolic process, because that particular molecule of ATP goes from something larger to something smaller. And metabolism is the total amount of anabolic and catabolic processes in the body. So this chapter is going to be talking about the gasoline that we use for our body, in particular exercise, or the difference between, maybe resting state and exercise fuel, and those substrates that are involved with that. But I think before we can talk about that, really what we need to do is maybe address this whole notion. I'm sure you guys have heard of this energy in and energy out. All right. And if we're trying to like maybe potentially discuss weight management or increasing muscle mass, energy, let's make that Y into a G, energy in equals energy out. And I'm not going to write the out part, the energy in equals energy out. And right now, if we have energy in equals a particular amount and we're spending the same amount of energy out, then potentially you probably won't lose or gain too much weight, but these are things that it's not so cut and dry. For instance, it's the kind of energy that you bring in and the kind of exercise that you do can really affect this whole energy balance equation. Furthermore, you might think of energy in. Energy in is eating, all right? And energy out is exercise. And eating is a behavior, all right? Eating. And you could say that an individual who has too much body mass or body fat could be eating too much, right? And the out is exercise. And they don't exercise enough. These are behaviors, right? And eating and exercise, those behaviors could be influenced by things, right? They could be influenced by all sorts of different advertisement or social pressures or so many different things. For instance, I wonder if Drew's on with us. Drew is on with us. Hey, Drew, my man, can you do me a favor and just take your hat off and just wave it at the screen for just, maybe 5 seconds? Yeah, so Drew's going to take his hat off. Look, he's waving it. He's waving it. He's waving. All right, that's good. Thank you, Drew. So that was a behavior. All right, Drew clearly performed a behavior, but the behavior was elicited by some type of external cue. For some reason, because I hold this professor position over Drew, I knew that if I asked him to hold his hat in front of the camera and wave it, that he would do so. Right. And then Drew, because he doesn't know what I'm asking him to do, and I'm the professor, he's like, okay, I guess I got to do what he asked me to do. So he takes his hat off and he waves it in front of the camera. I knew he was going to do that. All right. But that's a behavior that Drew did that was elicited by some type of external cue. So sometimes the behaviors that we undergo or that we perform are behaviors that aren't necessarily things that we're necessarily cognitively driving, or they're not necessarily our ideas or real intentions. They're driven by external cues. So it could be the case that this eating behavior, or in the case of individuals who might be morbidly obese or have too much energy and they're eating too much, and then this is also a behavior. Exercise is a behavior. So maybe this eating and this exercise thing, or this energy in, energy out, are behaviors that could be affected by the environments or the things that we're exposed to. And that's more than reasonable to think about. So maybe I'll go into a little bit more about that. And I'll stick with Drew. Why not? All right. If I have a lion, Drew, and a lion finds prey or it kills prey on the savannah, is it going to eat a dollop of the prey, or is it going to try to eat as much of it as it can?
Probably as much of it as it can.
I mean, because that lion doesn't know when it's going to come up with prey again. It doesn't know when it's going to find the next meal. So there are chemical processes that go on that as soon as the lion starts to eat the prey, there are hormones, and the hormones get into the bloodstream, and the blood is no doubt going to go to the brain. And when the hormones get to the brain, it tells the lion, don't stop eating now. The more it eats, the more it wants to eat. All right. It's going to start gorging itself on the food because of this, um, because of inherent need to eat and make sure that it has fuel. And then Drew, after you're done eating a turkey dinner, or after that lion is done eating that prey, what's it going to do?
Probably sleep or rest.
Probably sleep, right? Again, because the lion doesn't want to spend the energy immediately. Once it gets the energy, it wants to cache some of that energy or save some of the energy for later. So these two behaviors, eat more, and then sleep afterwards, they're not necessarily like a free will decision. Those behaviors are potentially modified or enhanced or even maybe caused by hormonal interactions upon that lion eating that prey. And your body particularly is very similar. And right now, I mean, humans have been around for millions of years. I mean, that's just an estimate. I don't really know human evolution or whatever, but they've been around for quite a long time. And it used to be the case that humans were hunter gatherers, like they would have to search and forage and hunt and trap their food. And in reality, when it was like a wild human situation, we never knew when we were going to get our food again. So when an animal or when a human was able to find a cache of, say, carbohydrate, its biochemistry kind of made it so that that animal wants to eat more carbohydrate, because carbohydrate is the best fuel for human beings. All right. So it used to be the case that like a human would come across some type of like amount of food, and just like the lion, there would maybe be some hormonal interactions that would make it so that that human would eat more and it would rest afterwards. And then when your body ingests sugar, what happens is the pancreas releases insulin, and insulin gets into the bloodstream, and insulin has a lot to do with the storage and the utilization of those sugars, and we'll get into that. But another thing that insulin does, not only does it get into the bloodstream and goes to the muscles, but it goes to the brain. And when insulin goes to the brain, it shuts down these two other hormones called ghrelin and leptin. And ghrelin and leptin make it so that you feel full. But if insulin shuts down this full response, then it leaves it open for you to want to eat more and eat more of this carbohydrate, of this fuel for exercise. All right. So one of the byproducts of eating carbohydrate is this feeling that you have to eat more. That's why, like, even what Lay's potato chips, it's even their tagline. You can't eat just one, right? Or like, I mean, Drew, I don't know about you, my dude, but like when I have candy corn, that's the end of it. I'll have like four of them, and then I'll be like, all right, I need to have four more. Then I need to have four more until finally I have to like roll the bag up and take three or four different like rubber bands and put it around the bag and put that like over across the room so I don't eat the whole entire bag. And sometimes I'll feel like weak-minded, like I'm a stormtrooper or something, and like I just cannot control the urge to eat the carbohydrate. But I have to remember what that is that's a response to insulin, right? And I have to understand it's not like being weak, in terms of eating more. It's just this biochemical interaction that's happening that's making me want to eat more. So also when insulin gets to the brain, it has this effect of making it so that you become a little bit tired. All right, so sometimes at night I'll get home from the gym and it's like 9:15, I'll eat dinner, everything's good. I'm like doing work, and then I'll go have an ice cream sandwich or two. Whoops. And then I notice like after the ice cream sandwiches, I'm like starting to get tired on my couch and I fall asleep. It's always after dessert that you feel like lethargic, and that's mostly because it's a hormonal interaction with insulin and your blood and your brain and your insulin receptors and things like that. So this energy in and energy out, energy balance equation that I guess supposed to sit up in front of class and teach, it's not that easy, because eating is a behavior that can be caused by so many different things, and exercise is a behavior as well. So what we have to do is maybe find the root cause of the behavior that's making it so that most people eat too much and they don't exercise. 50% of the country by questionnaire will tell you that they don't exercise daily. I'm a professor of exercise physiology and I don't exercise. I'm not trying to say that as like a badge of honor, but that's in all reality. Most people are that you're going to work with are not going to be exercising daily. And they also have issues with obesity and eating too much and not exercising. And I don't know if it's because these people are lacking willpower, or whether or not they'll infiltrated in their diet and in their advertisement by things that are going to promote a high insulin concentration in their bloodstream. And most of the products that we have are pumped with sugar and corn syrup and high fructose corn syrup and all sorts of different sugar additives to make the food taste better. But there's a byproduct of that, and the byproduct is these behaviors that might lead to to other morbidities like obesity and other things like that. So there's a little bit more to the equation here. So what I want to do is I want to give everybody just a little bit of an understanding of this energy in and energy out. I was going to show you this website called Calorie Lab, but when I went on it this morning, I couldn't find it. So one of the best ways for me to be able to track energy in is MyFitnessPal app. Has anybody ever used that? Hands up if you've ever heard of it or used it. Maybe I'll go to it. Sydney says she's heard of it. MyFitnessPal app. It's really good. Sometimes I'll probably end up having you guys do this too. I think I do in this course is have you guys do a 2-week food diary, and it's difficult. It used to be much more difficult when you didn't have MyFitnessPal app because you'd have to measure everything out. But using an app is much easier. But it's sometimes it's a rude awakening how many calories you actually are eating. And then I used to live with my old roommate, and he kept telling me he and his lady were going to try to lose weight. And I was like, all right, bro. So like he started kind of telling me his plan, but then when I went home and I watched what he ate, I mean, he was housing food, housing and ice cream and this and that. And then he kept telling me that I don't eat enough. And I was like, all right. So I tried to figure out how much I do eat. And then when I looked at my my MyFitnessPal app, I was eating a good 3,000 calories and I didn't even know I was eating 3,000 calories. And then so if I'm eating 3,000 calories and he and his lady are eating more than I'm eating, then they were pumping like 5,000 calories and couldn't lose weight. And I was like, well, I mean, maybe you should just be more accountable about what you are eating. MyFitnessPal app is really useful, but if you're not very accurate with it, you can miss 500 calories a day pretty easily. And that makes it so that your calculation of one half of this equation is off. And if you're using food diaries to help manage weight for your clients and you're off 500 calories a day, I mean, that's going to be significantly difficult for you to do your work. So what's difficult about this balancing of this energy in and energy out equation is accurately representing how much food you're eating. And the research says that people usually underestimate the amount of food that they're eating by about 2 to 4-fold. And it's difficult to figure out how much exercise or how many calories you're spending every day. And for the most part, people are going to overestimate how much exercise they do by 2-fold. And here's another problem. Like, there's really no way to tell you how much energy I'm eating, right? Like, if I go to Subway and I get a tuna fish sub, like, how much mayo is in that? And when they take a scoopful of that, like, tuna fish, it's about, I guess, an ice cream scoop, but sometimes it's more, sometimes it's less. Or when you go and you get a bacon, egg, and cheese or something like that from the school cafeteria, how much butter did they use to put that, on the grill? And so it's really difficult to be very accurate. And because of that, it makes our job as maybe nutritionists or exercise scientists or physical therapists or whatever, a coach or something, it makes it really difficult to use this energy in and energy out relationship with 100% validity. All right. So what I'm going to do is maybe give you a little bit of a head start in this energy out part. I'm not going to show you the energy in part because we'll do that later as part of our assignment. But I'm going to go to this website here. Let me go like this. Whoops. Let me undo that and go to the mouse and go here. And we'll go to our health-calc.org. 1 second. So that's a pretty cool website here. It's health-calc.com. Get all these drawings. And if you look on it, there's a bunch of these different cool calculators. There's a total energy expenditure calculator. There's a body mass index. There's a waist to hip ratio, a push-up test, calculating your ideal body weight. So if I had a client and I was doing like consulting work, I would do all of these stuff, these tests. White, right? I just go to each one of them. There's an Astran rhyming fitness test. I don't have a bicycle ergometer, so I'm not going to teach you the Astran rhyming fitness test. We're going to do the Queens College step test. All you need is like a stare. But any event, there are these pretty cool tests that you can go. But this one here, this total energy expenditure calculator, is really useful, I think. So maybe I'll go with Drew, and then maybe somebody else will help me too. So what I want to do is I just want to show you like how much energy you're spending on a daily basis. And this is the easiest way for me to show you. There's another way to do it too, like your resting metabolic rate, this basal metabolic rate. Let's do this as a little experiment here. So if I do this, there's an equation here. Your resting metabolic rate. This is like one of the most important equations, I think, in all of, I guess, nutrition. Resting metabolic rate is equal to 500, and you should write this down, plus parentheses 22 times your fat-free mass in kilograms. All right, so let's go through this. Fat-free mass, and we'll just make a note here that this is kilograms, because that'll make a big difference. If you do it in pounds, it won't work. So kilograms. So now what does this mean? Well, I'm 165 pounds, so 165 pounds, and I believe I divide 165 by 2.2, because there's 2.2 pounds per kilogram. So 165 divided by 2.2 is equal to 75. I'm going to do the math one more time. 165 divided by 2.2 equals 75. So I am 75 kilograms. All right, 75 kgs. So that means that the amount of energy, this is resting metabolic rate, RMR, a resting metabolic rate. And you'll notice here it says basal metabolic rate, so they're a little bit different. A basal metabolic rate is the amount of energy that your body needs to burn. If I was like laying supine in a lab room for 24 hours and no eating, fasting, and I'm just laying there breathing. This is the amount of energy per day that my body needs for my lung function, my heart, my circadian rhythm in my eyes, any processes that I'm making aside from not beyond rest. All right. It's really difficult to measure because you have to have people like in that lab room and fasted. And so typically we don't measure basal metabolic rate. We use this resting metabolic rate. They're somewhat similar, maybe, off by a couple of calories, but they're pretty similar. Resting metabolic rate is much easier to measure. In fact, it's so much easier to measure, I can measure it with this little equation here. So 22 times 75, 22 times 75 equals 1,650. So 1,650, and I'm going to add 500 to that. 1,650 plus 500 is equal to 2,150 calories. So my resting metabolic rate is 2,150 calories. So I'm going to erase this stuff here. All right. I'm going to erase all this. I'm going to erase this number here. I'm going to erase this number here. So if I'm going to just be pretty much sedentary during the day, I'm spending 2,150 calories. So let's set this to where I'm at and see how close this body calculator is. So right now I am 44 years old. By the way, you're going to go from 21 to 44 real quick. So make sure you save your money. All right, so I'm about 165 pounds. And notice if I change the body weight here, there's a big change in total energy expenditure because muscle burns fat. So if I build muscle and I get stronger by building muscle, I'm going to burn more energy. So sometimes we think getting on a treadmill is going to be the thing that's going to help with weight management, but it's actually, I believe, what I would teach you guys, it's the strength and conditioning that you do. And that's going to build muscle mass. And if I have more muscle, there's more place for the carbohydrate that I'm ingesting to go to. and then I can burn excess carbohydrate. The excess sugar that you eat, if you eat excess sugar and don't exercise the sugar off, the sugar is stored. It's like if you have excess money, you put it in a bank. And I watch TikTok, right? So these banks, right? This is where you storing all your excess carbohydrate as adipose fat. All right. So what you want is you want muscle mass to burn the excess carbohydrate so you don't store it. All right. I'm 5'8". So these are my criteria. Now, intense exercise. I don't do any intense exercise. Moderate exercise. I mean, some days I'll do a half an hour of biking. All right. Like 3 days a week. Light exercise. I'm in the gym a good amount, spotting my guys. So let's say I'm in the gym and I spot for an hour. All right. The rest of the time I spend in the gym, let's say it's another 4 hours. I'm never sitting down really. So I'm always walking. And then let's say I walk another half an hour during the day. And usually I get about 7 hours of sleep. All right. One thing you should notice is like if I do get, let's even say 8 hours of sleep. All right, if I get 8 hours of sleep, and notice as I sleep, right, it increases the amount of calories because your brain's still working. All right, so let's say I get 8 hours of sleep. That means with all these numbers, I'm sitting 10 hours a day, so it takes me, I sit 2.5 hours when I'm teaching you, and then I have to get into the car and drive another hour there and another hour back. That's 3-4 hours. Seems like sitting 10 hours a day is a bit much, right? But you see right here that I'm spending 3,000 calories every day. Now it says my basal metabolic rate is 1,746 calories. Our resting metabolic rate was estimated with that equation at 2,150. Again, that's about a 400 calorie difference. So that's something that's reasonable. So whether or not you use this equation or that equation, all right, you'd have to justify either one. I like the 500 plus 22 times fat-free mass because I don't even need to have one of these calculators with me. But you'll notice that with the minimal amount of exercise and activity that I'm doing, I'm still spending 3,000 calories. So if I'm not eating 3,000 calories, the remaining calories is coming from somewhere, right? And so the remaining calories are coming from my body tissues, my muscle mass. And if I keep doing this and spending 3,000 calories, but eating 2,000 calories over the course of time, I'm going to become a thin old man, right? And just use my muscle mass slowly but surely for energy. Oh, actually, you know what? Yeah, that's right. All right. So what I want to do is maybe just get a different understanding of maybe somebody or two other people from class and maybe be able to go through this so we can see sort of how much calories you guys are spending on a regular day. And then it'll give us a little bit more of an understanding when we're talking about ATP and calories and what we need to bring in and what we're spending. It'll give us a little bit more of a valid understanding of chapter 2 when we go through it. So does anybody want to volunteer to give me their info? Is there anybody who does like sports, who works out like daily? All right, Morgan, I see you. Morgan, how old are you? First of all, we'll switch it to the ladies' side. And how old are you?
20.
You're 20? All right. So 20.
138.
138?
Yep. And then 5'4".
5'4". Okay, so in order for Morgan to just like literally be alive without eating her own muscle and tissues, she needs to have at least 1,400 calories. We'll talk about percentages, but about half of that, 50% of your diet should be carbohydrate. And sometimes people go on a no carb diet, or there's diets that are low carb diets. To me, especially with exercise physiology, exercise or sports physiology, to me, I think it's critical to have carbohydrate because it's carbohydrate that your brain uses for energy. And if you don't have carbohydrate, then what's going to happen is your brain is going to use your fat stores and they're just going to transfer it to the byproduct of metabolism, which is acetyl-CoA, and it's going to go through the Krebs cycle just like carbohydrate would. So your brain is going to switch pretty much protein and fat, if it doesn't have carbohydrate, to carbohydrate so that it can have energy through like glycogenolysis gluconeogenesis. So your brain needs carbohydrate anyway. So if you go on a low carb diet, one of the reasons they don't work is because people just get mentally exhausted by the end of the day and they can't keep up the diet. All right, so I think that carbohydrate is fuel. It's like gasoline, right? If you don't have gasoline in your body's not going to just like hibernate. It's still going to function, but it's going to find some other gasoline. It's going to find something else to burn, and the only other option is your own body's tissues, and you don't really want that. All right, so right now, Morgan is spending about 1,400 calories just being alive. So Morgan, how much intense exercise do you do on the reg?
Yeah, I said for an hour for the intense.
So an hour, and I mean, look at now, this is an hour of intense exercise, and now she's up to 3,300 calories. All right, but then you might say, oh my goodness, I don't want to eat 3,000 calories or 3,300 calories a day. Morgan, how much moderate exercise?
30 minutes.
30
It's the
minutes,
same. And then I did like 30 minutes for light exercise.
30 minutes for light exercise, standing and walking.
I did 4 hours with like classes and stuff.
All right, so she's regardless at about 3,180 calories. When you might say, well, 3,000 calories, I don't know if I want to eat 3,000 calories, or I don't know if I should be eating 3,000 calories. I mean, if you're trying to do this 1 hour of intense exercise and you're not meeting these 3,000 calories, then unfortunately what's happening is some of those calories are coming from the very muscle that you're trying to build, right? Or the fat stores that you need in order to make sure that you have good thermal regulation as you're running outside in the winter. You know what I mean? So now this is if you want to maintain homeostasis, if you don't want to build any muscle. If you want to build muscle though, you're going to have to add probably 250 to 500 calories on top of these 3,000 calories. So if Morgan's in her off-season hypertrophy phase, Morgan, what sport do you do, dude?
I play soccer.
So I mean, if
So
she,
I'm in off season right now.
and I'm sure you guys are lifting. I'm just going to get a sip of water. 1 second. I'm sure you guys are lifting, right, Morgan?
Yeah, we are, or we will start the semester.
So I mean, if she's trying to get gains, I'm sure you're trying to probably put on like 3 to 5 pounds of muscle mass, right? That's probably the goal of your.
I mean, yeah, I should be. I not necessarily want to, but I should be.
I mean, so how about like instead of 3 to 5 pounds, you put on a pound, or just 1 pound or 2 pounds of muscle mass. I understand not trying to like gain weight or whatever, but you know, like even when you're losing weight, Morgan, like I don't even think that losing weight actually equals losing pounds off of your body. I think the real goal for somebody who's trying to lose weight is to stay the same weight, but switch the fat that they have to muscle mass. Right? So let's say that you're just trying to like maintain, Morgan, or like maybe gain 1 pound of muscle mass. You know what I mean? You're still going to have to at least be a little bit more than 3,100 calories. And that's not even 3,100 calories. It's actually because of the 80 there, it's more like 3,200 calories. So if you're not meeting 3,200 calories, it's 1,500 calories about in carbohydrate each day. 1 second, hold on. And then if I take a look at like my rice-a-roni here, like rice-a-roni, and I take a look at how many calories as prepared, there's 3 servings in this box. And this box right here has 250 calories. So 250 calories per serving means that in this box, there's 750 calories. So to meet your 1,500 calories, you'd have to have 2 boxes of rice-a-roni a day, which is pretty easy to do. And then you have also this family, hold on, I'm gonna go like this real quick. Stop the share. And I'm gonna go like this, stop the video, virtual background. Just get rid of this so I know that when I'm showing you guys stuff, you can see it. So this stuff, I'm sure everybody's seen these brown rice. First of all, you should be housing these if you're doing sports, like housing them 3 a day, right? 4 a day. At least that's what I was doing when I was competing. A little bit of soy sauce on top. But these ones right here, this is amount per serving is 180 calories. All right, and each serving is one serving is 180 calories. 1 second, and there's 3 servings per bag. All right, 3 servings per bag. So 180 times 3, that's 540 calories in one of these brown rice bags, these boiling bags. All right, so if you're trying to get to your 1,500 calories of carbohydrate, you gotta have 3 of these a day. So just so you understand what that is, okay? So 2 of these or 3 of those brown rice things, all right? All right, let me go share the screen again. Let's go back to here. All right, so in order to get half of that, you're eating 3 big, brown rice bags of rice a day. All right, and that's if, Morgan, you're just trying to maintain, body mass and what you're doing. All right, so let's go. Is there anybody else who does sports or anything like that? Yeah, Aubrey, let's go with you. What's up? How old are you, bub?
I'm 20.
20, and how much do you weigh?
Like 160.
Okay. All right, and how tall?
5'6".
Right. Notice height doesn't do anything. All right, height's not changing anything at all. Right, and now this 160 pounds, when you change it, you can see obviously the total energy expenditure is changing, but it's not necessarily going to be 100% accurate because we don't know whether or not the 160 pounds is 50% 50% fat and 50% muscle mass, or whether or not it's 70% muscle mass. We have no way of telling. So we can only, take the validity of this stuff so far. All right. But at the same time, even if I did skin calipers, there's only so much validity because the skin calipers, it's not 100% accurate. Right, skin calipers are plus or minus 3.5, percentage points either way. So I'm only going to get so accurate. So, and Aubrey, how much intense exercise?
I'd say 30 minutes.
And moderate exercise?
An hour.
Light exercise?
Probably 30 minutes.
Standing, walking?
4 hours is probably good too.
And sleeping?
I'd say 9.
I mean, one of the things to me I've always been really struck about is, so in spite of all this stuff, you're still sitting 9 hours a day? It's a lot, right? It's a lot. Yeah. And 9 hours a day on top of the 9 hours a day that you're already inactive by sleeping. So either this is a lot, or this stuff up here isn't as accurate as we might think it is. Maybe we're actually standing and walking for more like 8 hours a day and we just don't feel it. But in any event, all right, Aubrey's up to 3,378 calories. And if she's going to the gym and she's trying to make muscle mass happen, then she's probably going to have to be closer to like 3,000. Right now, that's 3,400 calories. So she's going to have to be closer to like 3,600 calories. So all of a sudden, the amount of calories that you need in starts to become a little bit more than you might have thought. All right. Is there anybody else who doesn't do much physical activity at all that wants to give me some info just so we can see a low end? Or is there somebody who does more? I want to see how high we can get this number. Is anybody who does like a lot more than this? Is there anybody who doesn't do anything at all? All right, so let's say you have a 20-year-old female who's 130 pounds. Let's even go 120 pounds. 5'6" is fine. Let's say no exercise at all. No exercise at all. Standing and walking. I mean, she's still at 1,800 calories. That's with nothing. right? And the more you sleep, like the higher that's going to go. So I think that the low end is about 1,800 calories, and that's why if you look on like your carton of milk, all of the calories that we have, all of the percentages, all of the recommended daily amounts and limits that are listed on everything is based on a 2,000 calorie diet. All right. So the average amount that people are spending every day is about 2,000 calories. 2,000 calories for females, and 2,200 calories for males. And that's probably way underestimated because for the most part, people are overeating. All right, so at least now you can use this calculator. I use it with my parents. Now what happens if I'm working with a kid and at the end of the day, he's starting to have behavior problems? Well, is he a little punk? I don't know, he could be, but he could also be starving. So let's go like this. I only teach boys. So let's go 11-year-old kid. 11-year-old kid's gonna weigh no more than 80 pounds. And he's going to be about 4'5", and we do a lot of exercise. Maybe we'll do a half an hour of intense but moderate exercise in the gym, at least about half of the workout he's going. So let's say 2 hours, and then the rest of the workout, let's say an hour here. And then during workout, he's, standing during his day, he's got school. So he's sitting for 6 hours a day on his online courses, and he's getting, 8 hours of sleep a day. Well, I mean, this 11-year-old kid is still pumping out close to 3,000 calories. But then I ask him what he's eating. He says, chicken nuggets, Skittles, orange soda, McDonald's, and Cinnamon Toast Crunch cereal in the morning. And that's all he eats. Literally, that's all he'll eat. Or like skinned hot dogs that his mom has to skin for him, so kids aren't eating. So we have these 2,778 calories. And during the off season, if I want this kid to put on a little muscle mass because he's going to be turning 12 and I want him to do some strength and conditioning, if he's not getting 3,000 calories, then a lot of the work that I'm going to do is for naught. It's not going to work. Or he's going to be exhausted, tired, and it's going to be this kind of like this downward, trending graph of energy until finally he's just, his immune system can't handle it and he gets sick. A lot of times in the gym, I just listen to what they say. And if there's a change in behavior or attitude or a change in willingness to do harder skills, or I notice cold sores or chapped lips or like it's just a look in their eyes or whatever, a lot of times these kids are not getting these 2,778 calories. So instead of spending calories doing strength and conditioning, I go to try to like save calories so that I can make it so that I can improve sport performance because they actually have calories. So do you spend the calories that the kids have? Well, I mean, if I need 2,778 calories and I'm eating 3,500 calories, then I have extra calories to spare on my strength and conditioning program. But if I need 2,778 calories and my athlete's only eating 2,500 calories, I have to reconsider whether or not the strength and conditioning program is actually going to be beneficial and whether or not I should have him do foam rolling and save calories to improve sport performance because he's not exhausted. So it all goes into this whole kind of play of whether or not the energy in and energy out is, reasonable, but I can't put all my eggs into that basket. Okay. So I think the low end right now for anybody really is about this 2,000 calories. So when you do your food diary on MyFitnessPal app, you'll notice that either you're way above what you think you are or you're way below it, and it will help you get a better understanding. You're going to have clients, and you're going to expect that your clients or your athletes are able to understand this and understand how to break down your bioenergetics and the substrates to be able to get to these values here. Let me go one more time. I don't know why Calorie Lab. Calorie Lab. This used to be my favorite. Calorie Lab. calorielab.org. Such a bummer. Such a bummer. It's such a good website. All right, yeah, it's not on anymore. Anyway, in the future, I'll have a couple of other things that I can show you in terms of energy in, energy out, and I have this really. Maybe I'll show you on Wednesday another website that I use. It's called the Exchange Program. The Exchange Program is a way. Now, if I tell a parent they have to get to 3,200 calories, it's not good enough for me to just tell them that they have to get to 3,200 calories. I think it's probably, as a professor or a teacher of things, it's probably important for me to be able to give them a technique or a way that they can get to those 3,200 calories. So I'm just plugging my computer in. I have to be able to give people some type of method or some type of guide to get to the 3,200 calories. All right, and I'll show you that probably on Wednesday. All right, so let's go to, let's get into the chapter. We'll have a little bit of fun with the lecture. All right, give me a second here. Does anybody have any questions about that? All right, well, here we go. All right, so we started with the beginning of chapter 2. We're talking about fuel for exercise. All right, the fuels for exercise are called substrates. And the three main substrates that we're talking about are carbohydrate, fat, and protein. Now, the way that you want to think about it is carbohydrate is gasoline. Protein is like metal. It's like what you would make the car out of. You would make the car out of, you know, leather and foam for the seats and rubber for the tires and steel. And if there's like a car fire, the first thing that's going to explode is the gasoline. But then once the gasoline explodes and the fire is hot enough, it's going to burn the rest of the car as well. Right? So you can burn protein, you can burn the fat stores in your body, but you don't necessarily want to. You want to make sure that you're burning carbohydrate, but then there's different forms of carbohydrate as well. Right? There's some carbohydrates that like cotton candy. When you put cotton candy in your mouth, it literally just dissolves instantaneously. Or when I drink apple juice, like the carbohydrate in the apple juice is in liquid form. There's nothing to break down. It gets into your belly and instantaneously it's absorbed pretty much. So if I drink a glass of apple juice or orange juice and there's like 100 calories in it, that 100 calories goes into my bloodstream in minutes. And now I have this whole huge amount of carbohydrate in my bloodstream, and my pancreas is like, oh my God, what am I going to do with all this sugar? And the pancreas has to work really, really hard to make enough insulin so that the insulin can attach to the sugar and bring it to the muscles. And eventually your pancreas just breaks, and that's what type 2 diabetes is. All right. If it's either your pancreas breaks or the receptors for insulin along your muscle fiber cell walls, the receptors start to become deactivated. So you need more and more and more and more and more and more insulin. And eventually you just can't keep up with the amount of sugar that's in your body. Your body can't store the sugar in your liver and in your muscle as glycogen, or it can't store enough of it as adipose fat. And what happens is the sugar starts to pool up in your blood. And that's the indicator that you have type 2 diabetes, is when your blood concentration of sugars increases. So we want to use carbohydrate as fuel. We want to use protein to make your body and your tissues stronger. And we want to use fat. Fat, remember, fat is really important. Fat is the basis of a number of cellular interactions. Like you remember, there's fat soluble vitamins, A, D, E, and K, that you can't ingest and absorb into your body without fat. And all of your cell walls are fat and phospholipids and lipid bilayers, and your fat stores keep you warm when it's cold and help you with thermal regulation, and also padding for your organs and stuff. So fat is important. And actually, fat is a good way to store excess carbohydrate, excess fuel, but you want to keep the fat so that you can maintain cell walls, integrity. And so if you don't have any carbohydrate, your body certainly will use protein and fat for fuel. All right. The problem is most people don't exercise. So if people aren't exercising and they have excess carbohydrate, then that's the problem, because insulin is going to take excess carbohydrate and it's going to change it to a stored, a good storage form of calories. And the best way to store calories is in fat, because fat, you can store more grams of, or more calories per gram of material in fat. We'll get to that later. So. Then later on, we'll talk about how this energy production is controlled, and it's controlled with enzymes. And then we just talked about storing energy, all right? Your body really doesn't store a lot of ATP, adenosine triphosphate, but you can make a lot of adenosine triphosphate with these energy systems. And again, here's systems. Here's the word systems again, right? And what emerges from these energy systems, what emerges from that is the amount of energy that you need for those cross bridges to change their orientation, for your heart to keep going, and for your lungs to keep going, and for that basal metabolic, those basal metabolic needs to keep functioning. Now, within these energy systems, there's more than one way for your body to get energy. So not only do you have the phosphagen system and the glycolytic system and the oxidative system, but those systems all interact with each other to make like kind of another order of system. So how these systems interact with each other, how these systems are constrained to each other, and what emerges from that is probably bioenergetics. All right, so the substrates that we're going to be talking about all break down into adenosine triphosphate. It's an adenine group with 3 phosphates, and the phosphates are held together, and they're also held to that adenine group with chemical or electrical bonds. And when the bonds are broken, then energy is released. And that energy is actually used directly by those myosin cross bridges, where the myosin heads attached to the cross bridge. There was that ATP binding site, and ATP kinase to break down the ATP into the adenosine diphosphate to the free phosphate group, and that release of energy is what we use as fuel. All right, bioenergetics is the process by which all of these carbohydrate, fat, and protein molecules are broken down so that we can gain ATP. We can't store too much ATP, all right? But we can make ATP from other things. We have this carbohydrate, fat, and protein, and one of the biggest evolutionary benefits of animals on this planet is that a long time ago, these really small microorganisms realized that with fuel, with carbohydrate or fat or protein, and oxygen, which is in our air, we can use carbohydrate, fat, protein, and oxygen and water to create more ATP than you could possibly store within your body. So that's what we do. We utilize oxygen as human beings, and fish do it, and plants utilize carbon dioxide to make energy. And good thing that those gases are in our air, because that's pretty much catalyzed all of our life on this planet. All right, the term metabolism we talked about earlier refers to all of the chemical reactions in the body. You have chemical reactions that break things down, like the breaking apart of adenosine triphosphate into adenosine diphosphate, and eventually adenosine monophosphate, but you also have anabolic processes that build things up, like when you have adenosine diphosphate and remnants of a phosphate group, and they combine, all right, to make ATP. So there's chemical processes that are going both ways, breaking them down, building them up, and the combined process is called metabolism. So the amount of energy in any particular amount of food, or for that matter, the amount of energy in actually any activity that you do. Let's say I'm walking. If I'm walking, I'm spending energy, I'm releasing energy. And you could put an individual in what's called a calorimeter, a direct calorimeter, where it's like this big chamber, and in that room is a treadmill, and surrounding the room is this intricate layer of pipes that has water in it. And when I do activity, it's going to increase the temperature in the room, and that's going to increase the temperature on the water and the pipes that surround the room. And I can estimate the amount of energy or the amount of heat energy that I've spent doing that bout of walking by measuring how the increase in temperature of the water. That's called a direct calorimeter. You can also do direct calorimetry in regards to the amount of food that you're eating. So you could take like a slice of white bread, put it into a calorimeter, burn the white bread, and the increase in temperature of the water is related to the number of calories that is in a particular food product. And that's pretty much how they've figured out all of the caloric amount, or the amount of calories in each of the food products that you're using. All right. So and something that's a little bit confusing is sometimes this calories and kcals is used the same way, although this K implies 1,000, and typically 1,000 calories is 1 kilocalorie. All right. But they also call this 1,000 calories 1 calorie, which if is a capital C, it means the same thing as kilocalories. It's kind of confusing, but really kilocalories and calories are used interchangeably, which is kind of weird. I don't know why they do that. Anybody have any questions about anything so far? All right. So let's get into the types of substrates that we have. All right. We typically are going to burn carbohydrate, fat, and protein. And the amount of carbohydrate that you want to burn in a typical diet is 50% of your diet. 50% of that 2,000 calories should be from carbohydrate. 50%. What does that mean? Well, that means if I have 2,000 calories a day, 1,000 calories should be from carbohydrate. And remember, one of these boxes here is 750 calories of carbohydrate. Now that's probably also, let me just see, this is not 750 calories of carbohydrate. This is actually 41 grams times 4, 41 times 4, this is 1,600 calories of carbohydrate in this, right? Because you have 250 total calories, but there's butter and all sorts of other stuff that's giving you calories. So this is for what did I say? 41 times 4, 160 calories. This one right here, there is nothing else except for carbohydrate in this, I'm pretty sure. So this is 180 calories. This is 540 calories from carbohydrate. All right, one of these things. So about 2 of these things each day to get you to your 2,000 calories. Then fat, you want to have about 30% fat in your diet. And that's not just 30% bacon grease, because there's different kinds of fat. There's saturated fats and non-saturated fats. And some of those fats are different in terms of how they affect your cholesterol levels. And cholesterol is kind of important, like high density lipoproteins and low density lipoproteins. Those are typically the types of cholesterols that we'll talk about. Low density lipoproteins, you don't want to have those. Those are no bueno, because low density lipoproteins, they're so small that they actually fit under the cell walls of your blood vessels and veins. and they kind of like start stacking underneath the cell walls, and it starts to push the cell walls kind of away from each other, and the cell walls start to like get thicker and thicker, and eventually it causes plaque, and it causes narrowing of your arteries and veins, and then you have a heart attack. But the high density lipoproteins, those are so big that they can't fit under the cell walls, and they're so big and heavy actually that what they do is they knock the low density lipoproteins out of the cell layers of your blood vessels and arteries, and actually makes it so that the low density lipoprotein can get back to your liver, and when it gets to your liver, it's made into more glucose for later on. So you want to have fat, and then protein. You don't need too much protein actually. The amount of protein that you need on a daily basis is 2 cans of tuna or 2 chicken breasts, right? So if you eat a lot of egg whites and chicken breasts and think that that's going to make you bigger and stronger, it's not the case. In fact, protein is unique because it has a nitrogen group on it. And that nitrogen group has to be taken off of the protein molecule. It's an amino acid, an amine group. The amine group needs to be taken off of that protein before it can be utilized, and that actually costs the body energy. So it costs the body more energy to use protein. So the body doesn't want to spend energy. So the body doesn't want to use protein for fuel. It's only going to use protein for fuel when it has nothing else. And excess protein is going to be either broken down as amino acids and go through the Krebs cycle anyway, or it's just urinated out. So excess protein is not stored by the body anywhere. The only way to get, like, excess protein doesn't make muscle. What makes muscle is testosterone and insulin-like growth factor and growth factor in females. And what makes muscle is intense enough exercise to cause micro damage to the muscle, and then the body is like, whoa man, I need to like repair this broken down muscle or else I'm going to get injured. And it's more of a hormone process than it is an eating process. All right, when you're resting, you're using about 50% carbohydrate and 50% fat. Carbohydrate is fuel, and when you're resting, you're not spending a lot of calories anyway. So your body doesn't mind using fat as fuel because you're not going to really waste away all of the fat stores at rest. And your body wants to save the carbohydrate for later because it knows that during short bouts of exercise or even longer bouts of exercise, your body's going to want to use the carbohydrate. So the more physically fit you are as well, the more capable your body is of using fat at lower intense exercises and holding on to that carbohydrate stores so that you can do your longer bouts of activity. All right, so carbohydrate is money. It's money in the bank. If I gave you, like gasoline is $2.29 a gallon. If somebody gave me an extra 10 gallons of gasoline, I would probably take that extra 10 gallons of gasoline and store it. I would put it in my garage, right? It's like a commodity. So carbohydrate is a commodity that your body doesn't want to get rid of. And what it does is it stores the excess carbohydrate, all right? Excess carbohydrate is going to be attached to insulin. It's going to go to your liver, and your liver is going to change the excess carbohydrate to muscle and liver glycogen. But your body can only store so much muscle glycogen. When it can't store any more muscle glycogen, literally your cytoplasm gets full of muscle glycogen. What happens is your body changes the carbohydrate to some other way to store energy, and the other way to store energy is by changing it to adipose fat. So adipose fat, the fat underneath your skin, is stored carbohydrate. All right, the less muscle mass you have, the less opportunity carbohydrate has to go to muscle. And if you're not doing any physical activity, the carbohydrate's going to go to the muscle and it's not going to be used anyway. So no muscle mass and no activity equals more stored carbohydrate. And that means more adipose fat. So again, if you're, oh, hey, actually, you know what? I made a small mistake. Just to clarify, All right, I did make a small mistake, just to clarify. And let's just redo this math. All right, it's 500 plus 22 times your fat-free mass. So fat-free mass is your muscle mass. So muscles, all right, utilize energy, resting metabolic rate. The amount of energy that I spend even just being alive is related to the amount of muscle mass that I had. But I said I'm 160 pounds and I'm 75 kilograms, but I forgot that's 75 kilograms. Remember, my basal metabolic rate according to the thing was 1700, but we calculated it as 2100 or so, 2150 or so. But that 2150 seems like an overestimate compared to the 17. It's because I forgot. This is just my total kilograms, but I'm about 20% body fat. So if I'm 20% body fat and I'm 75 kilograms times 0.2 equals about 15 pounds of that, 15 kilograms is my fat mass. So 75 minus my 15 equals 60. So my fat mass is actually 60 kilograms. So 60 times 22 is equal to 1320, and add 500 to that, I'm at 1820, and that's a far better estimate. So 1820, all right? And this number actually is wrong. But I think that maybe what's important is that the more muscle mass you have, the more energy you're spending. Because for the most part, the carbohydrate is going to the muscle to get spent for energy and fuel. Let me get rid of all these drawings, okay? Let's go to the next slide. Anybody have any questions so far? All right, so carbohydrate is sugar. A carbohydrate is a molecule that is comprised of a carbon, a hydrogen, and an oxygen in some manner of amounts. So you could have simple carbohydrates, you could have more intense polysaccharides, disaccharides, those are all sugars. All right, for every gram of carbohydrate, you have about 4.1 kilocalories. Now, you'll notice for every gram of fat, you can store 9.4 kilocalories. So why would your body store things in a substrate that can't store as much energy? So if I have 1 gram of carbohydrate, I can only store 4.1 kilocalories. If I switch that to fat, then I can store more than twice the amount of energy in the same amount of material. So what happens is your body is going to switch all of your excess carbohydrate to fat. And you also just don't have enough space in your liver and in your muscle cells to store a lot of carbohydrate. You only have enough for about 2,500 kilocalories. That's why you need to eat carbohydrate every day, because you just don't have enough to store. All right, but like I said before, carbohydrate is the primary source of energy for your brain, right? So if, like sometimes I'll see people falling asleep in class, but it's like 10 o'clock in the morning. Unless people are going to like raves until 6 o'clock in the morning, they shouldn't be tired at 10 o'clock in the morning. So if I notice that like people are falling asleep in the back of the room, it's not because they're tired. It's probably because they don't have enough carbohydrate. Or if it's 7:30 in the evening and my kids are starting to go off the wall, I don't think it's because they're poorly behaved. I think that probably at 7:30 at night, they're completely exhausted, tired, and their brains don't have any carbohydrate in them. Right? So you need to continuously eat carbohydrate so that you can replace those kilocalories that are spent each day, because you don't have the opportunity to store carbohydrate. All right, but this carbohydrate is transferred into other things like glycogen. Muscle glycogen in your liver and muscles gives you a little bit of stored carbohydrate, and then glycogen. I don't know if you remember, but I said lysis means cutting in half of, so hydrolysis, hydrolysis, right? When you have ATP, in order for the ATP to break down, it breaks down through hydrolysis, all right? Well, same kind of word, glycogenolysis. Glycogenolysis is when your body stores extra glucose in your liver and muscles as glycogen. And then if there's not enough glucose in your bloodstream, then your body will cut this glycogen in two through glycogenolysis. And that glycogen is stored in your liver and muscles. Much more is stored in your liver than your muscles. But that glycogenolysis will make it so that stored glycogen can get broken back down into glucose so that I can use the glucose from my muscles and brain and have energy. Okay? But again, I really don't have enough stored carbohydrate and glycogen to not rely on those stores. Now, if I don't have muscle glycogen or glucose, then what's going to happen is your body is going to want to use those 70,000 kilocalories plus stored in your body. And it says plus there because there really is no limit to the amount of fat that an individual can store under their skin. And I'm sure that you've seen the television show like My 600-Pound Life or the 1,000-Pound Sisters. I mean, there literally is no limit to the amount of fat that can be stored. And the reason why your body does that is because of this number right here. Fat is just a better storage, strategy than storing things in carbohydrate. Now, you can store more than twice the amount of kilocalories in the form of fat. Imagine if your body couldn't switch to fat. Imagine how big those individuals would get now. They'd be even bigger than they've gotten in terms of obesity. All right, so what your body does is it uses oxygen to switch your excess carbohydrate stores to fat. Again, like if you gave me $1,000, all right, I might be able to fit $1,000 into my pocket, right? If you gave me $10,000, I'd be able to fit that $10,000 in my pocket too. But eventually you're going to give me so much money that I just can't fit it in my pocket and under my mattress, but I'm not getting rid of it. What I'm going to do is I'm going to bring it to the bank, and they're going to change it from cash to money in the bank. And your body is the same way. Your body doesn't want to get rid of excess sugar. Excess sugar is excess gasoline, excess fuel. Your body wants that. So it's going to keep it as long as it can. It's just going to change it to a different storage system, right? So it's just changing it to stocks, right? This is your body's stockpile of carbohydrate. Saves it, and when it needs it, it can burn this fat either through beta oxidation and the Krebs cycle, or it can go through what's called gluconeogenesis. Gluco is sugar, neo is new, and genesis is making. Gluconeogenesis. Making glucose from other things that are either left in the body from the breakdown of ATP or from fat stores that are in adipose fat. Typically, fat is going to be the substrate used for very long and low intense exercise. And the more physically fit you get, the more your body is going to want to use fat and save carbohydrate. So sometimes you'll see, right now in terms of weight management, again, I think it has a lot to do with the resting metabolic rate equals 500 plus 22 times your fat-free mass. Fat-free mass. So if I can get my fat-free mass, which is my muscle mass, to increase, that estimate of resting metabolic rate increases. So I want to increase my muscle mass, And I don't want to get on a treadmill and do necessarily high intensity interval training, because it's the less intense exercises that are burning fat, because my body wants to save carbohydrate for the higher intensity exercises, especially if I'm working out and I'm fit. So I would say it's probably prolonged low intense exercises, like just walk on a treadmill, 35, 45 minutes, 3 days a week, and do 2 or 3 days a week of strength and conditioning and getting those muscle mass to increase. And that's a better way to spend energy, or to reduce caloric, or to increase caloric outtake to target fat stores. All right. Now, with fat, you would think, wow, my body can store so much fat. Why don't we use fat as a fuel prior to carbohydrate? Well, carbohydrate breaks down much faster. All right, it takes a lot for these free fatty acids and the glycerol. Like, you have a triacylglycerol. Your fat in your body is stored as triacylglycerides. Triacetyl, and a glycerol. So you have, like, fat kind of looks like this, where you have this glycerol backbone, all right, and then you have these globs of fat. These are your glycerols, or your free fatty acids, and they are attached to this glycerol backbone, right? This is your glycerol. And in order for your fat to be used as fuel, this fatty acids right here need to be broken off of this glycerol backbone. These fatty acids are going to go to the Krebs cycle. First, they're going to go and do beta oxidation and get broken down. And then these free fatty acids are going to be used to make ATP in the Krebs cycle. Or in this glycerol backbone right over here can be used to make more fatty acids in store, or can get broken down in gluconeogenesis, eventually can become these carbohydrate stores that your body might need if you don't have any more fat, right? So you can go backwards. All right, so let's clear all of this stuff here. All right, so this is showing like how much liver glycogen you have, how much muscle glycogen, and how much sugar is in your body fluids. All right, so if you look, your body doesn't store too much glycogen in the liver, stores much more muscle glycogen, and you don't really have too much glucose in your body fluids at all. That's why you have Gatorade. Gatorade is a fast burning form of glucose. It's one of the reasons why you want to have Gatorade as opposed to Powerade, or as opposed to a Monster energy drink. An energy drink doesn't have glucose in it. An energy drink has caffeine in it. And if you look at statistics, caffeine is definitely associated with increased sport performance, and it's actually statistically a valid increase in sport performance. But for my athletes who are all, young kids, I don't want to tell them to have caffeine and artificially increase their heart rate in order to give them energy. I want to make sure that I'm giving them energy because they have, sugars. And Gatorade actually has straight up glucose in it. It doesn't have high fructose corn syrup. It doesn't have other forms of sugar. It has actual glucose in it. So I tell my athletes who are spending those 4,000 calories, make sure you keep the glucose in your body fluids by having about, a Dixie cup worth of Gatorade every 20 minutes while you're working out. And that's how I can manage the amount of carbohydrate in their body fluids. But at the same time, you'll notice, even if I have the most that I can, it's probably about 3,000 calories in the body here, even less than that, of carbohydrate. But I can, in my subcutaneous and the fat around my organs, I can store way more than that. So the storage form of fat in the body is much more efficient, but it takes much longer to burn down the fat than it does for the carbohydrates. Much more difficult for your body to burn the fat than it is carbohydrate, so your body uses carbohydrate. The last energy substrate that we have is protein, but you really do not want to be using protein for fuel. And you don't really store too much energy in protein. You'll notice it's 4.1 kilocalories per gram. And if I look back over here to carbohydrate, it's also 4.1 kilocalories per gram. So your body's not going to be storing excess protein if it doesn't need it for actual muscle. The reason why your body is going to store protein or increase the size of your muscle is because of micro damage during workout. And when your body thinks that the muscle is breaking down, your body is like little like army ants is going to go to the muscles and try to build it back up and build it back up. So if you can trick your body into this never ending break the muscle down, then the body will continue to build it up and build it up and build it up. And that's where you get, really big weightlifting muscles. But for the most part, I want to manipulate my athletes out of hypertrophy phase, as the summer training ends anyway. So eventually there's going to be an end to the size that muscles can get, especially with ladies because of hormones. So in any event, your body doesn't really want to be using protein for fuel, although it can, but it needs to be converted into sugar anyway through a process called gluconeogenesis. All right. You can also switch protein to fats through lipogenesis. Genesis means building of, and lipo is fats, or the beginning of. So the beginning of fat from protein stores. So the reason why these keto diets work is if I don't have any carbohydrate in my diet, my brain needs to have some type of fuel so that it can function. So it's going to change the protein that I eat into free fatty acids through lipogenesis, and it's going to take those free fatty acids and pump them into the Krebs cycle, make those free fatty acids into acetyl-CoA, and then I can go through the Krebs cycle and get energy and ATP. So if I don't have any carbohydrate, then I can use my protein stores for my for energy, for my brain, for my muscles. But again, I think that one of the reasons why you don't want to do that is because breaking down protein costs the body energy, and it's just going to make it so it's more difficult for that process to occur. So in order, especially for individuals who would, like Morgan, who are trying to go through off-season hypertrophy training, you want to make sure that you guys are burning carbohydrate and not protein. So you have food intake. Your substrates are fats, carbohydrates, proteins. For the most part, we want to take in carbohydrate, and carbohydrate is glucose. Glucose is a molecule that has 6 carbons, all right, 12 hydrogens and 6 oxygens, C6H12O6. And that glucose can go through, it can be stored in your glucose pool. It can be stored in your body, your bloodstream as glucose, and that glucose can be used by your body for energy, or it can be changed, glycogenesis, glyco, all right, glycogenesis, all right, glycogenous, all right. It can be turned into glycogen and stored as glycogen stores, or your glucose can be in the form of glycogen. The glycogen can be lysed or broken in half, and that glycogen can become part of your glucose pool. All right, and that glucose can be broken down into remnants, all right, and utilized for energy. Or I could eat fats, triglycerides, all right. It's a glycerin with 3 fatty acids. Those fatty acids, those 3 fatty acids can get broken down. They can become part of your free fatty acid pool, or it can be stored as fat. That fat that's stored could be broken in half through lipolysis, or the free fatty acids can go through lipogenesis, the creation of fat, and go to the fat stores. So same thing, proteins are going to eventually be broken down into amino acids. Those amino acids are going to go through the Krebs cycle and become part of your amino acid pool and go through gluconeogenesis so that they can create sugars, or those amino acids are going to be stored as protein in your body, but those proteins can eventually be broken down into amino acids and can all eventually go through the Krebs cycle. So the end product of all of these substrates is going to be the Krebs cycle. And the Krebs cycle, except for actually carbohydrate can get broken down outside of the Krebs cycle through fast glycolysis, and we'll talk about that in a couple minutes. Anybody have any questions? I know there's a lot of information, but we're recording it. You can always go over it. Any other questions? All right. 1 second. All right, so all of these substrates are not available right away. Remember, last class we talked about the difference between type 1 and type 2 muscle fiber types is in one of the enzymes called ATPase. And ATPase is an enzyme that helps control how fast ATP is broken down and the availability of the energy that is produced by metabolism. So the more ATPase, the easier it is to break down that ATP, all right? And sometimes excess enzyme make it so that those energy systems or substrates are going to be broken down before others. So ATPase is one of the rate limiting enzymes that controls the speed of this particular chemical breakdown of ATP. And typically what an enzyme is going to do is it's going to make it so that in order for ATP to be able to use, it has to get broken down. But like, let's say, for instance, I want to push someone over, all right? This is the first example I thought of. If I just like, you know, flick them with my little index finger, it's not going to be enough energy to move that person. Like for Drew, if I wanted to push Drew over, I mean, I guess I could like maybe push him with one hand, but he's a strong guy. It might not be enough to push him over or move his feet. But if I go over and I shove him really hard, and he's first of all going to get annoyed with me, I'm going to trigger him. So how much pushing on Drew, all right, is enough to trigger him? Well, if I push him a little tiny bit, it's probably not going to do too much. If I push him a little bit more, it's probably not going to do too much. But if I push him enough, it's going to trip him into a different kind of like energy state where he's going to fall over and get annoyed. All right. You could think about the amount or the intensity that I have to push him is my activation energy. How much am I going to push him to get him to act? Right now, I mean, I might have to push him a lot, but if he's really annoyed, I might not have to push him at all. What happens is with these enzymes, it makes it so that Drew will become more triggered easily. All right, so it takes less energy for me to actually like trip him over, like, you know, to get him to be annoyed. That's what an enzyme does. Typically, this breakdown of ATP requires a particular amount of energy. But with the enzyme, the amount of energy for the breakdown of ATP into ADP is much less, and I can get to that usable energy without spending as much energy. All right, so an enzyme is going to make these enzyme catalyzed reactions happen much faster and with less spending of energy. And I can get the same product. I can get the same amount of usable energy out of it. So enzymes help make all these products happen a little bit easier. And some of these steps, like ATP breaking down into ADP, requires ATPase, but then when you go into the Krebs cycle and you see other aspects of these, of ATP breaking down, there's an enzyme that needs to do that in order for this carbohydrate to break into the next thing. There's another enzyme needed, another enzyme needed. So along the way, there are these enzymes here that end up making it so that like even down the line, the byproduct of this breaking down with this enzyme makes this, and this is another feedback loop that affects how much enzyme 1 I have. So down the chain, the product of chemical interactions can also be a feedback loop for enzymes that are at the beginning of the breakdown cycle. So these are called a feedback loop and based on enzymes. And if I don't have enough enzymes, then I'm not going to be able to break down those substrates fast enough for energy. So, all right. So typically the energy that you have is going to all be coming from the breakdown of ATP into ADP, adenosine diphosphate. So ATP is an adenine group. It's and it also has 3 phosphates, and those phosphates are ripped off of that adenosine triphosphate molecule. And when that happens, there's a big release in usable energy. And that energy is going to be utilized by your myosin heads and the myosin cross bridges to change their angle and reattach to your actin heads so that you can have a sliding filament theory. And when the sliding filament theory occurs, or when the filaments slide across each other, you have muscle contractions. So ATP is needed for muscle contractions to occur, and therefore ATP is needed for your body to be able to move. All right, ATP is broken down by hydrolysis. Hydro is water and lysis is breaking down. So ATP goes through a process of hydrolysis and combines with the enzyme needed for this particular interaction to occur, and it's broken down into ADP plus P plus this release of energy. All right, and then ADP is also at times broken down into AMP, adenosine monophosphate, and you can get some energy from that, but it's far less useful, and there's not as much of that going on than there is ATP. All right, and then what can happen is ATP can get recreated, right? So I have adenosine diphosphate plus phosphate, and I can combine some energy there, and that can get broken down into anabolized into ATP, and this is through a process called phosphorylation. One of the things I should say is that this breakdown, ATP plus water plus ATPase, not all of this energy is used by the muscle. In fact, I believe it's only about 20% of the created energy or the released energy is actually used to do any muscle movement at all. 80% of the energy that is created in the breakdown or in the catabolism of ATP is lost in the body. And that's lost in the body in the form of heat. And that's why you shiver. Because when you shiver and your muscles are moving and it's breaking down ATP, you have all of this lost energy that's seeping through your tissues and it makes you warm. All right. Some of these synthetic or synthesizing of ATP from the byproducts doesn't need oxygen. In fact, some of the utilization of ATP by carbohydrate or the breakdown of carbohydrate into ATP does not require oxygen, and we'll talk about that in a second. But some of the glycolysis or the breaking down of glucose for energy does require oxygen.
I have a quick question.
Yeah, of course. Go for it, Tatiana.
Can you go back to the last slide a second?
Can.
Thank you. So when you're talking about shivering,
Yeah.
When you get a chill, is that just like a brief form of like a shiver that kind of does the same thing, or is that like another process?
I mean, I would say probably a chill is more a factor of the hypothalamus, right? Your hypothalamus is your internal regulator of thermostasis, right? Of heat equilibrium, right? So I would say it's probably more a function of that, or it could be a function of like it's cold in the room. But I would say that the human, or just the human, the mammalian way of dealing, or one of them is of dealing with being cold, is by shivering. I don't know if fish shiver, or if like a monitor lizard that's cold, a cold-blooded animal shivers. I'm not 100% sure, but I would say like a chill is probably more a result of a hypothalamus change in either hormone regulation or something like that. Okay. By the way, I don't know everything, so all of the answers that I give you are like my best guesstimate, but I can't say that I'm right about anything, and I can't say that I'm right about all of the answers that I give you, just for a disclaimer. I can only answer the questions with the amount of knowledge that I have. For the most part, I'm wrong. I don't even know I'm a professor, but for the most part, I'm wrong. All right, so bioenergetics, basic energy systems. For the most part, you're going to be using ATP, but ATP, you really don't have enough ATP. I mean, we already showed you, you only have a small amount of glycogen stored in your muscles, where we really don't have too much ATP stored on our body, but it's kind of good because we can create it a bunch of different ways. You can use the remnants of ATP and phosphocreatine You can use ADP and phosphorus and energy and water to create ATP. That's called your ATP phosphocreatine system, the phosphagen system. And that doesn't take oxygen. It's anaerobic. All right, there's also a glycolytic system. Now, glycol is, glycogen or sugar. So there's a sugar system. There's a way that you can use sugar. And again, system, 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 systems. All of a sudden, this dynamic systems theory starts really resonating with me. And I started paying attention to the terms and to things that I'm learning. Then I started thinking maybe it's the systems approach that's more powerful than thinking about the hierarchical motor programming approach. But anyway, here's more examples of systems. Now, what emerges from point A and point B is length. But what emerges from the glycolytic system, the oxidative system, that the ramifications of that question are pretty powerful. This oxidative system is different than the ATP and the glycolytic system because in the oxidative system, as the name implies, I'm starting to use oxygen. The oxidative system is where your carbohydrate, protein, and fat is going to be broken down in the mitochondria. So let's go start talking about this. So I can get ATP from what's called the phosphagen system or the phosphocreatine system. This phosphocreatine system doesn't require oxygen. All right, so if I'm holding my breath and I'm, doing 5 jumping jacks, then most likely I'm using this ATP phosphocreatine system. But then what happens is in those 3 to 15 seconds of activity, all of the phosphocreatine that is stored in my body is going to be burnt. So then what happens is you have to rest and you have to regenerate or resynthesize or recycle the ADP and extra phosphorus back to ATP. So now think about my athletes in the gym. My athletes in the gym, like on vault, a vault is only going to last about 15 seconds. They run down and they do a vault. A pommel horse routine is only going to last for about 30 seconds, maybe 40 seconds. A rings routine the same. And the longest that a routine is ever going to last in gymnastics is about a minute and 10 seconds on floor. So when they're on vault, they're using this ATP phosphocreatine system. So one of the things that I do is I try to work their body's ability to use this system and this system alone. Because if I have my athletes work the oxidative system, they're never actually going to be running for, that period of time. Most of the time I can do a whole pommel horse routine holding my breath. Sometimes in a meet, I'm so nervous that I do so. So I don't want my athletes to get better or to necessarily get appreciably better at using this oxidative system. I want to figure out a way to make my gymnasts work on this system here. But I think Morgan said that she does soccer. All right. So I would say that Morgan probably wants to work more at this system here, because in soccer, you don't have really line changes. I think Morgan's going to probably play the whole game because she's great. So she's going to be playing for 45 minutes at a time. So I need Morgan to work her oxidative system. But I don't know, Drew, what do you do, bro? Lacrosse, I think?
I'm on the hockey team.
Oh, so exactly. So the hockey team is different. The hockey team is going to go for about 2.5 minute shifts. So the hockey team is going to be going for 2.5 minutes. Morgan's going to be going for 45 minutes. And my athletes in the gym are going for about 1 minute. So if I have everybody run for 45 minutes a day, I'm not going to train my athletes in the bioenergetic, in the system that they need in order to burn fuel. So with my athletes, what we do is we do ATP phosphocreatine system training. What they'll do is they'll do battle ropes, like you tie a rope, one of those heavy ropes around like the base of the pommel horse, and they'll go up and down, left and right, jumping up and down, jumping left and right, smash, 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 spin, 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 spin the other way for 35 seconds, 100% effort. And then what I'll do is I'll give them I'll give them, they'll go for twice this, they'll go for 30 seconds. And usually I'll do more than that, because if a routine is about 30 seconds long and floor is about as long as a minute, I'll have them go for 1 minute straight. And then what happens is it takes time after I burn all of this ATP, it takes time for this ATP to be replenished. It says you replenish ATP stores during rest. So after about 30 seconds to a minute of maximum exercise, 100%, all of this ATP is broken down, and you need this phosphocreatine, creatine phosphate, all right, to start your ATP recycling. And what'll happen is with this rate limiting enzyme, this enzyme called creatine kinase, the phosphocreatine that's in your body after the breakdown of your ATP will combine, and it'll start to make your, it'll break down this phosphocreatine into creatine plus phosphate, and there's energy that's released. All right, and then that energy can be used to reassemble ATP. So there's like this big recycling process that goes. So I have them go for a minute, totally burn all of their ATP, and then spend 4 to 5, 7 minutes. It's usually about 5 to 7 minutes you need for an untrained individual to recycle all this ATP. But then what happens is if we keep training that, a minute on, 4 minutes off, 1 minute on, 5 minutes off, 1 minute on, 5 minutes off, then what happens is you notice slowly but sure they're gassed. After that 1 minute of battle ropes, they are gassed. And in the beginning of the summer, when we start training or sort of end of the summer rather, when we start training this, they're gassed for like 5 minutes. But slowly but surely you can see they sit down, they foam roll, they're sucking wind. And then after about 4 or 5 minutes, they start getting ready and moving around, ready to do their next bout of their fast glycolysis or ATP phosphocreatine system training. And slowly but surely that 5 to 7 minutes turns into 3 to 5 minutes. And my hope is when they do a vault and they run down and they burn all their ATP, by the time they get to parallel bars warm up, I want all the ATP stores to be rejuvenated. Then they warm up, they'll burn all their ATP out, and before they compete, I want them to rest for 3 to 5 minutes. And in that 3 to 5 minutes should give them plenty of time to recycle their ATP, so at a meet, they're ready to go. So I'm manipulating the ATP phosphocreatine system. Sometimes my athletes will say, should I run during the summer months? And I say, well, I mean, not to utilize energy better. The only reason I would have my athletes run is because if they run, they're going to increase the strength of their heart, increase the size of their lungs, increase the ability to use oxygen. And if they can increase the ability to use oxygen, then we'll be able to use oxygen better for this ATP phosphocreatine system, right? And for any other fast glycolysis and slow glycolysis they need, and tissue remodeling and things like that. So I'm only having them do endurance training so that I can improve cardiovascular health, not so that I can train them to use their bioenergetics more effectively in gymnastics. But for somebody like Drew, I would probably have him do glycolytic system training, all right, which is going to be different than this kind of training, all right. For glycolytic system training, I probably would do things like underwater swimming, or I would do sprinting, 30 seconds to a minute sprinting, or I would go like all out for 2 minutes, and then I would rest for 3 minutes and all out for 2 minutes. Drew, I don't know what kind of aerobics do they have you working on in off season for hockey?
We usually do a bunch of Olympic lifts, but we do like all of our aerobic stuff is all sprints. So
right. So I mean, I don't think that would make any sense for Drew to be running for 45 minutes on a treadmill. And I would bet, because you're doing power training and strength and power training, I bet that, I mean, I don't know to what extent you guys work with your strength and conditioning specialist, but Drew, do they tell you that they don't actually want you to do a good amount of long distance running?
yeah, we don't do that much long distance running at all.
Right, because if you look at the research, long distance running and long-term endurance training actually has a caloric cost to it, because most part people aren't getting to their 4,500 calories eating. So Drew is going to do all of his power training exercises trying to get stronger and bigger quads and bigger glutes. And then he's going to do his long distance running and sap the very protein stores and muscles that he's using. So it's counterproductive to what Drew would be doing. Right, but then we're going to talk to Morgan, and I bet Morgan is doing more. They probably have you, Morgan, on either, you know, an elliptical, or probably doing something like probably doing running on a treadmill or doing a rower. Right, they're probably doing some long distance or long-term aerobic work. Is that correct there, Morgan? Well, we'll assume that maybe she's making eggs or something like that. But anyway, you can manipulate your workouts to train your body's ability to use energy differently. And if you're not doing that, then, you know, if I have my guys work their oxidative system, when they go to a meet, they're going to be gassed. Will they be able to run and play soccer with their friends on Saturday? For sure. But when they go to a meet, it's not going to work very good. All right, so other things about this phosphocreatine system is for every mole of phosphocreatine, this is actually like the energy substrate that you're going to use. It's the rate limiting enzyme. It's the rate limiting enzyme because it's the phosphocreatine that is breaking down with creatine kinase to give you this energy to make ATP again. So you can kind of think that in this ATP phosphocreatine system, that phosphocreatine is the fuel. All right, so for every mole or for every unit of phosphocreatine, you're going to make 1 unit of ATP. It's like a 1-to-1 carryover. Probably this is the kind of system that like the smallest organisms back in the day used, but then the organisms realized that they don't have to use phosphocreatine. There's other things that they could use, right? In any event, this phosphocreatine system is only used for the first 3 to 15 seconds of energy. And usually we're doing longer than that. So in order for humans or in order for those organisms to get out of the sea and start to, you know, be able to get bigger and procreate, they had to be able to do things that lasted longer than 3 to 15 seconds. All right, so we had to do some other thing aside from this ATP. Organisms did, multicellular organisms had to do something aside from this to reassemble ATP. And for the most part, because this turnover of ATP is so small in the phosphocreatine system, your body actually doesn't use it for energy too much. What your body really uses this ATP phosphocreatine system for is to recycle ATP. So when I do burn the ATP down with that 3 to 15 second of maximal exercise, and you think of like, you know, most of the activities that you do on a daily basis, they don't really last longer than 15 seconds. Like if I got to go like put like a shopping bag in my like car, it lasts about 8 seconds. Or, you know, like if I'm pushing the shopping cart from the holding area in the parking lot into the store, it's a, you know, most daily activities last about this time. So you really don't need to have too much ATP stored, because you're going to do this activity and then you're going to get in your car and rest. And while you're resting, these ATP stores are replenishing. So this phosphocreatine system is not so much about the breakdown of the ATP in this 3 to 15 seconds, but it's about the recycling of the AP during your rest, so that when I have to do this next bout of 3 to 15 seconds, I don't have to use my carbohydrate stores and spend all this oxygen. I can just use that recycled ATP. So this phosphocreatine system is more of like this recycling catch-22. You know, you spend it, you recycle it. You spend it, you recycle it. If you spend it and there's not enough to recycle, or I don't have any of this creatine kinase, then I can't really recycle, which is why people usually take creatine monohydrate, because creatine monohydrate gives you the creatine part, and the extra phosphorus from the breaking down of the ATP can create this phosphocreatine and creatine kinase, which can lead to energy, which can lead to faster synthesis of ATP during rest. So for my athletes, if I was going to suggest one sports performance, what is it, a substrate or dietary supplement. That's what I'm looking at for a supplement. I would suggest my athletes potentially use creatine monohydrate. Now, I would bet that maybe Drew, did your coaches tell you that you should maybe use a little bit of creatine monohydrate or no?
Technically, we're not allowed to for NCAA. So no.
Really, NCAA has said that creatine. Well, one of the reasons why is because it works. Right? They wouldn't have any problem with it if it didn't work. And when I was in the NCAA back at UMass, they gave us creatine monohydrate. Use this stuff. It's good. I never really used it, but now I would bet that Morgan's coaches really don't say too much about the creatine monohydrate, right? Because she's not really working at the ATP system too much, so I don't think that they've probably suggested that to her. Unless what they do is during hypertrophy and strength training, during the off season, they might suggest to use that as a supplement. But I didn't know that it was banned from the NCAA, so I guess you can't do that. But it works. All right, in any event, in this system, you have your phosphocreatine. It's going to be broken down to free energy, and that free energy is going to be used to combine ADP and phosphorus to regenerate ATP, and then again, boom, the ATP can be used for energy by the myosin heads. One of the big issues here is if I don't have enough phosphocreatine, or this actual regeneration of ATP here drops significantly as the time of activity increases. And the reason why is because my body just cannot keep up with the demand of phosphocreatine. So when the ability for my body to use phosphocreatine to create ATP starts to drop because the concentrations are so low, then I can no longer use ATP or this phosphocreatine system to create ATP, and eventually there's a drop after about 15 seconds. So I got about 3 to 15 seconds where I don't need to start using sugars for fuel. All right, so now we have the glycolytic system. The glycolytic system is glyco. Glyco is glycogen, and lytic, lysis, the breaking down of glycogen system. And your body is going to store carbohydrate in the liver and in the muscle cells in the form of glycogen. So really the glycogen system or the glycolytic system is an anaerobic system. It doesn't require oxygen. And the breakdown of this glucose is not occurring in the mitochondria. It's occurring in the cell wall, in the cytoplasm of the cells. All right, oxygen is not involved. And now with the glycolytic system, when you compare it to the phosphagen system, said here that the phosphagen system, for every mole of fuel, you get 1 mole of ATP. Well, I have no idea how this happened, but slowly but surely, organisms realized that if instead of using phosphocreatine, if instead of using the stuff that's stored in our body, if we start using substances that are in our environment, then we can actually make more ATP. So what happened is amoebas and little cellular animals started to eat sugars. And when they eat sugars, the ATP yield is about 2 to 3 times the amount that you can create using the phosphagen or phosphocreatine system in your cells alone. So instead of eating their own cells for fuel or using processes within their own body or using and catabolizing substances in their own bodies, these microorganisms started to catabolize substrates, catalyze fuels of other sources, and a great fuel was sugars, carbon, hydrogen, and oxygen. All right, now those sugars are usually used, or the glycolytic system is utilized after the ATP is run out. After the 15 seconds of ATP, your body doesn't have any more ATP. It's got to use something else, and the something else that are mammalian oxygen, or actually not oxygen yet, but our animal, system can function with is carbohydrate. So for about 15 seconds to 2 minutes of activity, Drew, while he's on the ice, is using glycogen, glucose. That's one reason why in baseball they can have multiple games in a row, but Drew will only have what, two or three games a week at most,
Yeah, at most.
right? Because if he plays every day, what's going to happen is the amount of muscle glycogen and liver glycogen is going to deplete between each game, and the glucose that he eats in his food isn't going to have enough time to actually be transferred into muscle glycogen and stored. So slowly but surely, he's going to have less and less and less muscle glycogen, and then he is not going to be able to have as much energy. All right. It's also the case that Drew is usually going to have about a 2 minute to a 3 minute shift, I would bet, unless somebody's ill on the team, he's going to have to play more. But it seems as though right now, this is a little bit less than his shift. Why do you think that Drew doesn't play 5 minute shifts? Well, because he's training in the glycolytic system. If he's training in the glycolytic system, you only have enough muscle glycogen and glucose in order for about 2 minutes of activity. So when those 2 minutes are done, he's got to rest. Then his body is going to have to break down more glucose through glycolysis. And in any event, this is probably one of the reasons why Drew's hockey shifts don't last longer than, this 2 minutes here. All right. Also, if I want to keep training him, he could play. If he's playing pond hockey, he's probably going to play for an hour and a half at a time. But if you're trying to manage a team and you're trying to make sure that when you're working these bioenergetic systems, that you're actually making headway, it would make a lot more sense, instead of pushing him into his slow glycolysis, it would make more sense to have a bunch of people who are all training at this fast glycolytic system, so that they can accomplish these 2 minutes of activity without having to push into their oxidative system. So to keep, his team and the bioenergetics of his team functioning appropriately, it makes more sense to have a bunch of people working in the glycolytic system as opposed to only a few people working in the oxidative system. In any event, the glycolytic system is anaerobic. It does not occur in the mitochondria, and it can provide 2 to 3 times more ATP than the phosphagen system. That's why you don't need the phosphagen system to last for a long period of time, because after the 3 to 15 seconds, you have some other system that can take over. And this glycolytic system is going to use sugars or glycogen. All right, glucose has C6H12O6. All right, and it has to transfer all of those glucoses, all right, to glucose 6-phosphate. And eventually that glucose 6-phosphate is going to be changed to pyruvic acid. A pyruvate is this glucose molecule broken in two. So glucose has 6 carbons. And when that 6 carbon structure is broken in half, there's going to be a cost. It costs the body energy to break down glucose, 1 ATP. Now, your body wants to use muscle glycogen because it doesn't cost the body, all right, any ATP to use muscle glycogen, all right? And there is an energy cost breaking down glucose, but glucose, a 6 carbon molecule, is going to be broken in half through glycolysis, and it's going to end up as a pyruvate, pyruvic acid. Pyruvic acid is a 3 carbon molecule. And the breakdown of glucose into pyruvic acid, it doesn't happen in the mitochondria, but there are many different enzymes that are required for that to happen. And you're going to make 2 ATP molecules for every glucose molecule. All right, so before it was 1 ATP for every molecule of creatine phosphate. Now you have 2 ATPs for glucose. And because I don't have this ATP cost for the breakdown of glycogen, it's 3 molecules of ATP if I'm breaking down glycogen. So you can see here that this is where the 2 to 3 moles of ATP. If I'm using glycogen at 3, if I'm using glucose, it's 2. In any event, 2 to 3 times the amount of ATP using sugars is much more effective than this breaking down into 1 mole of ATP for phosphocreatine. Well, that's why human beings and other animals utilize sugars for fuel, because you get more fuel for every mole of this substrate. So it's a better thing to use. All right, so let's go take a look here. All right, the negative is that, like if I compare, now this is the glycolytic system compared to using the oxidative system. Now you have these molecules, they got out of the ocean, they get out of, that like and they start using a substrate. Oh boy, talk for 2 hours is tough sometimes. All right, so now the cons are, although you can get more ATP using sugar, you're still going to get less ATP if you use sugar and oxygen. So it's still somewhat inefficient in terms of using sugars, because when you combine oxygen, it makes for a greater ATP, like 33 times the amount of ATP. So although it's pretty good because it allows your muscles still to contract when you don't have a lot of oxygen. And it is better in terms of short-term higher intensity exercise than both using oxygen and the phosphocreatine system. All right, so it does give you 2 to 3 times the amount of energy as the phosphocreatine system, and you don't need oxygen. So if I'm like swimming underwater for, like, I don't know, 100 meters all the way across the pool, I'm clearly not using oxygen because there's no oxygen underwater, but I'm still able to function and still able to use my body to create energy because my muscles are moving. So when I'm swimming underwater, I'm utilizing this glycolytic system, and I'm breaking down any of the muscle glycogen and the glucose that I have in order for ATP. So the pros are I don't need oxygen, and I can do it a little bit longer than I can with the phosphagen system because I'm making more ATP. But the cons are, compared to using oxygen, it's not even close. You can make much more energy using oxygen. The phosphofructokinase is the rate limiting enzyme. When there's a reduction in ATP, there's an increase in PFK activity. All right, and that phosphofructokinase is also going to work with enzymes in the Krebs cycle to dictate how fast this ATP production can occur. All right, so glycolysis is about 2 minutes of maximal exercise. And if I'm going to do any other duration of exercise, like Morgan's work, then I'm going to have yet another pathway for creating ATP. And that's where we come to the oxidative system. And the oxidative system, as it seems to imply, uses oxygen. You need to have oxygen to break down ATP. This is an aerobic system. So now this is where I would want to train Morgan. Right, so I have 3 different sports: gymnastics, hockey, and soccer. And if I train all of my athletes the same way, then we could potentially do some of them a disservice. You think about a football team. A football team has all sorts of different needs on that team. You have a kicker. Kicker is usually going to be on the field for 15 seconds of activity, maybe even less. But you have a running back who's going to have to go for, probably 15 minutes. 15 minutes is usually a pretty long drive. That's going to get into the oxidative system. But you could have a wide receiver who's going to go for about, 2 minutes, and then he gets called off because it's first and second down. And so you could have different needs for different players on the same team in the same sport. So you have to just be aware of the fact that you want to not only train muscle and strength and flexibility, but you can manipulate and train bioenergetics. The good thing about using oxygen is now organisms, not only have they started to use external substrates for energy and sugars, But now they've also started to utilize the oxygen in the air, in the atmosphere. And when you use oxygen in sugar, now you can get 33 times the amount of ATP for 1 molecule of sugar. And when you compare that with the phosphagen system, where I only get 1 mole of ATP for 1 mole of phosphocreatine, all of a sudden using oxygen makes it much more effective to create ATP, 100-fold more effective than it does to use the phosphocreatine system. And now you see why oxygen and sugars and wheat and potatoes and the ability to gather grains became such an incredibly important part of the hunter-gatherer diet and the formation of more complex animals than slimes and tadpoles in water. All right. The oxidative system will last for hours because you can utilize fat, carbohydrate, protein, fat stores, free fatty acids, all sorts of different substrates for the utilization of oxygen in its creation of ATP. So this is the most complex of the systems by which living organisms get energy and fuel for movement. And this does not occur in the cytoplasm of the cells. This occurs in these specially designed cells, mitochondria, which you probably heard of as the energy or the energy factory of the body, these mitochondria. So mitochondria are very important in terms of the Krebs cycle and the utilization of sugars combined with oxygen in order for energy production. So stage 1 of the oxidation of carbohydrate, or stage 1 of the utilization of oxygen in the lysing or the breaking down of carbohydrate, is called glycolysis. And there's no difference between this glycolysis and fast glycolysis. So oxidation is the breaking down of sugar, but it takes much longer than the breaking down of sugar and the utilization of sugar to create ATP than it does in the glycolytic pathway. So although oxidation and this glycolysis here, the glycolytic system, they both use sugar. All right, this one here, the glycolytic system, this one here is referred to as fast glycolysis, the fast breakdown of sugar without oxygen. And this one over here, this oxidative system, is sometimes called the slow glycolysis. All right, it's still the breakdown of sugar, but it takes a lot longer. All right, it takes a lot longer because you got to go through the Krebs cycle. I'm not going to ask you necessarily every step of the Krebs cycle. Honestly, I don't even know it. And I think that people can probably get doctors on the enzyme interactions and step-by-step of how the Krebs cycle works, and also the electron transport chain. So by no means am I going to ask you to understand all aspects of that. But what happens is you have a sugar. The sugar is broken down into a pyruvate. The pyruvate attaches to a molecule of oxygen, and that oxygen brings that sugar into the muscle fiber, and in the muscle, it's already in the muscle fiber. And then the oxygen and sugar go into the mitochondria, and in the mitochondria, that pyruvate is broken down into acetyl-CoA with an enzyme called coenzyme A. And then like a bunch of different steps occur that allow it for all of these ATPs here, these 32 to 33 ATP per glucose, to be made. Now, if I'm using free fatty acids, this is fat. If I'm using fat in the oxidative system, specifically some fats, instead of 32 to 33 ATP molecules, I can get like 100 plus. So there are some like ultra fuels, like airplane fuels for the body that are created, like palmitic acid is an example of that, where they have 100 times the amount of ATP that the phosphagen system can provide. The reason why we don't use fats, though, is like we said before, it takes a lot longer to create energy from free fatty acids than it does to glucose. All right, so your body wants to use glucose. So let's get back to here. All right, so you have these glucose molecules. This is a 6-carbon molecule, right? That glucose is going to be broken down into pyruvate. All right, and that pyruvate is going to go into the mitochondria. It's going to release carbon dioxide when it breaks down into acetyl-CoA. This is the carbon dioxide that you breathe out. The acetyl-CoA is going to go through the Krebs cycle. The Krebs cycle is going to make it so that these NAD and NADH molecules release hydrogen. These hydrogen ions are going to go through the electron transport chain. They're going to combine with oxygen and with water to create ATP. All right, so, okay, so like we said before, glycolysis can occur with or without oxygen. Fast glycolysis is the breakdown of sugar without oxygen, but slow glycolysis is the breakdown of sugar with oxygen. All right. Now, the glycolysis here is going to be the same as this process here. This is the same process where sugar is broken down to pyruvate. This A box is the same thing that's going to happen with fast and slow glycolysis. And for each, it's going to make the same amount of ATP. All right. So it's the same general steps. The glycolysis part of oxidation is the same, and some of it can occur without oxygen. But with oxygen, the pyruvic acid is going to attach to the oxygen, and it's going to be transferred into acetyl-CoA. And then once it changes into acetyl-CoA, it's going to enter the Krebs cycle. And when it gets into the Krebs cycle, one molecule of glucose is going to lead to 2 molecules of acetyl-CoA. And these 2 molecules are going to go through the Krebs cycle individually. All right, so because of that, in the Krebs cycle, we're at least going to get twice the amount of ATP than we would get from 1 molecule of glucose, because that molecule breaks down into 2 things. It goes through the Krebs cycle twice. All right, not only that, but these 2 acetyl-CoA can make these GTPs, and a GTP is a guanosine triphosphate that acts very similar to adenosine triphosphate. So not only do I get the energy from these 2 ATP molecules that are created from these 2 acetyl-CoAs, but I also get the energy from this guanosine triphosphate. And that molecule of glucose is going to make these hydrogen ions, all right, from the NADH and the FADH. These hydrogen ions are going to go through the electron transport chain, and they're also going to result in a release of ATP, or the formation of ATP. What this GTP stuff does is it is really instrumental in making adenosine diphosphate and phosphate back into ATP. I believe that if I look over here, if you look over here on a more complex Krebs cycle chart, see this ADP changes back into ATP that I can use for energy. It's that GTP, the guanosine triphosphate, that is the rate limiting enzyme, or that makes this particular process happen faster. All right, so with oxygen and sugar, I can create much more ATP. Oh, here we go. All right, so here I got my pyruvate. My pyruvate is going to combine with NAD, and it's going to pick up this hydrogen group from hydrolysis from water, and it's going to release the rest of the oxygen and some of the carbon from the glucose in the form of carbon dioxide, and that's going to result in acetyl-CoA. Now, this acetyl-CoA stuff is kind of interesting, because when I break down fats through beta oxidation, and when protein breaks down through the removing of the free fatty acids, all the fat and the protein eventually is transformed into this acetyl-CoA. So this acetyl-CoA is kind of like this common denominator of metabolism. And once carbohydrate, protein, and fat breaks down into acetyl-CoA, all of them go through the exact same process and result in ATP. So you can use carbohydrate, protein, and fat as a substrate for your slow glycolysis, or for your oxidation. But again, we already discussed why the body would use carbohydrate for fuel and fat for storage, and protein for fuel only if I don't have any fat or protein. I mean, fat or carbohydrate. I don't necessarily need you to go through all of these, but you see there's 1, 2, 3, 4, 5, 6, 7, 8, a bunch of different enzyme reactions that occur. All right, when acetyl-CoA breaks down into, and it uses coenzyme A, it is transferred into citrate, and citrate with aconitase breaks down into isocitrate, and that is dehydrogenase. This is the hydrogen is removed from the isocitrate. That hydrogen goes to the NADH. It makes NAD plus turn into NADH. There's a release of carbon dioxide. This H molecule here goes to the electron transport chain. Same thing happens at this step. That H goes to the electron transport chain. Same thing happens. This GDP combines with guanosine diphosphate and phosphate groups that are left in the bloodstream to create ADP into ATP and energy. And then there's a release of carbon dioxide, hydrogens, water combines, another release of hydrogen, and then boom, the last thing that I'm left with is citrate synthase, and that citrate synthase combines with coenzyme A and acetyl-CoA that's coming into the Krebs cycle to make more citrate. So it's the Krebs cycle. It's a never-ending cycle of enzymatic interactions that allow for hydrogen to turn into ATP and for other ADP to be created into ATP and for this acetyl-CoA to result in a huge cache of ATP molecules. So for every glucose molecule that goes through the Krebs cycle, you're making 32 to 33 ATP molecules. It makes a lot of sense now why complex organisms use carbohydrate and sugar for fuel, but then all of a sudden these molecules stopped eating carbohydrate and started eating other animals, and those other animals had lots of fat on them, and when they did that, what happened is they started to make even more ATP. All right, but for the most part, our body wants to use carbohydrate for fuel because it happens and makes takes much less time. So like I said, you have all of these hydrogen atoms that can go through the electron transport chain, and when they do, there's even more ATP created because of this NADH and FADH. In any event, using carbohydrate and oxygen and fat and protein yields way more ATP, all right, than you would than it would yield for the phosphagen system. For every molecule of glucose, there's 32 ATPs, and then because glycogen doesn't cost that ATP, there's 33 units of ATP created for every 1 mole of glycogen. All right, now combine that with all of the NADH and all of the other ways that I can create energy through the Krebs cycle. I get 2 through just my phosphorylation. The electron transport's going to give me 5, blah, 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 another 5, another 15, another 3. So I have 32 total ATP created by 1 molecule of glucose. That's far better than the phosphagen system. All right, in terms of the oxidation of fat, all right, fat can sometimes be even more effective in terms of yielding ATP than glucose. But the reason why my body doesn't want to use fat is because it takes much longer for the oxidation to occur. There's another step. The glucose can be used directly, but fats are stored as triglycerides. A tri is a fatty acid, 3 fatty acids attached to a glyceride, a glycerol backbone. It's like the spinal cord of this fat, this vertebrae of the fat. Then in order for the fat to be used, the fat needs to be broken down into 1 glycerol, which is the glycerol backbone, and the free fatty acids. That needs to happen through lipolysis, but that takes time. It takes time because there are lipases. There are these enzymes that need to interact with the glycerol and the free fatty acids in beta oxidation for this fat to get broken down, or for the fat to be lysed, broken in half, so that I have my free fatty acids. These free fatty acids go to beta oxidation, and eventually they turn into that acetyl-CoA, but it takes a good amount of time for that to occur. The benefit is that you get 3 to 4 times the amount of ATP when you're burning fat, though. So that's a good thing. So we talked about beta oxidation is the process of converting the free fatty acids to acetyl-CoA. That happens before it gets to the Krebs cycle. So before the fat is able to be utilized, It needs to be transferred. And that costs the body a little bit of ATP, which is another reason why your body doesn't want to use fat for fuel as much as it wants to use carbohydrate, because it's an exogenic or exogenic interaction. It requires fuel. All right. And then depending upon the number of carbons on that free fatty acid or the complexity, you can yield more or less ATP. In fact, I think that they're going to say that this palmitic acid has so many carbons that by the time everything is finished, there's 106 ATPs yielded for each mole of this palmitic acid. All right, but everything eventually, all of this fat is going to break down eventually to acetyl-CoA and go through the Krebs cycle just the same as everything else would in terms of glucose oxidation. All right, so let's see where we're at. Oxidation of protein. Does anybody have any questions right now? We're literally almost done with this lecture, and I don't necessarily want to be all done with it. Does anybody have any questions? All right, maybe what I can do is, maybe I can stop here for today. I think that was about 2 hours and 25 minutes of straight talking. I think that if we don't have any questions, at least I can start here at a good beginning point for Wednesday. Wednesday, I'll finish what we're doing, but Wednesday we have our first IRAT and our first GRAT that has to do with chapter 1. So please be sure to review the chapter 1 lectures that I have on the YouTube channel. I hope that's helpful for everybody. And I can take a look at the analytics so I know how many people have viewed it. And right now, whopping 0 people have viewed it. So I would assume that everybody has all the information that they need. I will continue to record and post everything that's needed for the class. Does anybody need the book? Does everybody have the resources they need? All right, if you don't, let me know and I will hook it up. All right, but you know, scanning the book, the pages in the book, you know, scanning 45 pages takes me an hour and 15 minutes. You know, so if you have the book, that would be beneficial. And then I can focus on other things, okay? But if we don't have any more questions, I appreciate everybody's attentiveness. I look forward to Wednesday. I hope you guys enjoy the time that you have with the snow day and everything, and get your studying done. If you need anything, shoot me a quick text. That's definitely the fastest way. But if we're good for the day, then I hope you have a good day. Yeah.